Welcome to my channel Physics School Easy to Learn, and for more updates please subscribe, like and share my channel. Today we will discuss about class 12 physics chapter, that is ray optics, and topic that is linear magnification produced by a spherical mirror. Spherical mirror means that may be concave mirror or may be convex mirror, and in case of concave mirror we get real and inverted image if object is in between infinite up to focus, and we will get virtual and direct image if the position of the object is in between focus and pole. Similarly, in case of convex mirror we get always virtual and direct image. Clear? Then what is linear magnification? Suppose we take a concave mirror. Here outer surface is silver coated, so that is known as the concave mirror, and you draw the principal axis. Suppose this line is the principal axis, and this point, this is the pole, we write P. This point is the focus, we write F, and this point is the center of curvature, we write C. And suppose object is situated beyond the center of curvature, this one is the object, and for object height we write, suppose that is AB. AB is the height of the object, and suppose this is the first position of the object, then image is formed in between center of curvature and focus, and a small size image is formed. Small size means that is diminished, that. Clear? Similarly, suppose object is placed at the center of curvature. If object is placed at the center of curvature, this is the second position of the object, suppose, then image is formed also at the center of curvature. That means position of the object and position of image both are same. And in this case, size of image is equal to size of object, both are same size. And in the third case, suppose object is placed in between center of curvature and focus, this is the third case, then image is formed beyond the center of curvature and a large size image is formed. A large size or magnified image is formed. Clear? Look at the figure. In the first case, if we compare size of image with the size of object, a small size image is formed. Small size means that is diminished. In the second case, size of image is equal to size of object, both are same size. In the third case, size of image is large or greater as compared to the size of object, that means that is magnified. Clear? In first case we get a diminished image. In the second case we get same size or equal size image. In the third case we get a magnified image, that means size of image may be equal to or may not be same with the size of the object, so that we compare size of image with the size of object, and that comparison or ratio between size of image to the size of object, that is known as the linear magnification. Simply we write, for linear magnification we write symbol that is M. M is equal to size of image, we write size of image divided by size of object, that implies linear magnification M is equal to size of image, we write that is suppose H prime, this size. Size of object we write suppose H means A to B, that means finally we write linear magnification M is equal to ratio between size of image to the size of object, and this is the expression of linear magnification. Now we will calculate or we will derive expression for linear magnification both in case of concave mirror and also in case of convex mirror. First in case of concave mirror. And suppose concave mirror here producing real and inverted image. Here concave mirror producing real and inverted image. First we draw the ray diagram. Suppose here outer surface is silver coated, that is the non-reflecting surface, so that this is concave mirror. And we draw the principal axis. This one is the principal axis, suppose, and this point is the center of the reflecting surface, that is known as the pole. This point is the focus, we write that is F. This point is the center of curvature, we write that is C. And object is situated, suppose, beyond the center of curvature. This one is the object. And for object height, we write that is AB. AB the height of the object or size of object. For this we write suppose H. Clear? Then we draw two incident rays from the point B. First incident ray, that is parallel to the principal axis. If incident ray is parallel to the principal axis, you know after reflection the ray must be passing through the focus. Clear? That means if incident ray is parallel to the principal axis, this is the reflected ray. Reflected ray must be passed through the focus, you know that. Similarly, another incident ray is there. Second incident ray moves towards the pole. This is the second incident ray. And after reflection, the ray return back into the same medium. And this is the reflected ray. This one is the reflected ray. And here, both the reflected ray meet at this point, actually meet at this point. That means image is formed at this point. And that image is the real and that is inverted. This is the inverted image. Clear? And for height of the or size of the image, we write that is A1, B1. And for size of image, we write that is H prime. H prime is equal to A1, B1. Now, look at the figure. Here two triangles are there. First triangle, that is A1, B1, P triangle. We write that is triangle A1, B1, P. Another triangle is there, that is A, B, P triangle. We write triangle A, B, P. Now I compare these two triangles. We compare these two triangles and look at the figure. This angle is 90 degree, this angle also 90 degree. Similarly, this is the angle of incidence, suppose you write theta. This is also angle of incidence, sorry, this is the angle of reflection, we write that is theta. That means angle of incidence is equal to angle of reflection, both are same. That is the laws of reflection. Similarly, third angle of the first triangle must be same as third angle of the second triangle. So that we write both the triangles are similar. If both the triangles are similar, we write triangle A1, B1, P is similar with triangle ABP. If both the triangles are similar, then we take one side of the first triangle that is A1, B1, P. One side means we take A1, B1 side, and A1, B1 side is perpendicular to the principal axis. We take A1, B1. Similarly, from the second triangle means ABP. From ABP triangle, we take side AB. AB is also perpendicular to the principal axis. That means A1, B1 and AB both are perpendicular to principal axis. That means both are looks like similar. So that we compare A1, B1 with AB. That means we write A1, B1 divided by AB is equal to. Similarly, we take another side from the first triangle, that is A1, B1, P. Side is PA1. PA1 that is situated on the principal axis. Similarly, from triangle ABP, we take PA side. PA side is also situated on the principal axis. That implies we write A1, B1. A1, B1 is the size of the image, and for size or height of the image, we write that is H prime. And we put the sign convention. You know, below the principal axis, sign is negative. Above the principal axis, sign is positive. That is the sign convention. and the image is situated below the principal axis, so that is minus h prime. And for AB the size or height of the object. For this we write h, and the object is situated above the principal axis. Above the principal axis means sign is positive. Clear? That implies PA1 at point A1 image is there, so that P to A1, that is the image distance. For image distance we write V, but here this is the direction of the incident ray, and we measure from P to A1 just in the opposite direction of the incident ray. Opposite direction means according to sign convention we put minus sign, that is minus B, divided by PA at point A, object is there. We measure from P to A, that is the object distance. For object distance we write U, and this is the direction of the incident ray. We measure from P to A just in the opposite direction, and according to sign convention, opposite direction means sign is negative. That implies finally write minus minus cancel with each other. Here only one minus sign is there, so that we write h prime divided by h is equal to minus of V divided by U. Clear? That implies in place of h prime by h, that is the magnification. So that we write m is equal to minus of V by U. This is the expression for linear magnification in terms of image distance and object distance. Clear? Similarly, we will derive the expression for linear magnification in case of convex mirror. And always convex mirror producing virtual and erect image, always. And this one is the convex mirror. We draw the ray diagram. Convex mirror means inner surface, that is the silver coated. So that this is known as the convex mirror. First we draw the principal axis. This one is the principal axis, suppose. And this point is the center of the reflecting surface, that is known as the pole. Suppose this point is the focus, we write F. This point is the center of curvature, we write that is C. And an object is situated always in front of the mirror. Suppose this one is the object. And for object height, we write that is AB. And for AB, we write that is H. Clear? You know that. Now, we draw two incident rays from the point B. First incident ray, that is parallel to the principal axis. First incident ray, that is parallel to the principal axis. If incident ray is parallel to the principal axis, you know the reflected ray moves in this direction, and this one is the reflected ray. This one is the reflected ray. Clear? Similarly, another incident ray is there. Second incident ray, suppose it moves towards the pole, then the reflected ray moves in this direction, and here this is the reflected ray. This one is the second incident ray, and this one is the reflected ray. Here two reflected rays are there, and distance between the two reflected is gradually increased. Distance increase means both are diverging with each other. If both are diverging with each other, then both the reflected ray never cross with each other in this side. That means image cannot be formed in this side. So that we extend both the reflected ray in the backward direction. If we extend both the reflected ray in the backward direction, then what happens? If we extend this ray in the backward direction, you know the ray appears to meet at the focus. Why? Because incident ray is parallel to the principal axis, and if we extend the second reflected ray, both the reflected ray meet at this point. That means image is formed at this point, and you draw the image. This one is the image, and for height of the image we write that is A1 B1, and for A1 B1 we write that is H prime. Clear? Now we compare two triangles. Look at the figure. Here also two triangles are there, just like your first case. Clear? And triangles are that is A1 B1 P. We write triangle A1B1P, and another triangle that is ABP, we write that is triangle ABP. Now I compare these two triangles. Here look at the figure. This angle of the first triangle, that is 90 degree. This angle of the second triangle, that is also 90 degree. Both are same. Similarly, if this is the angle of incidence, suppose that is theta. This one is the angle of reflection, that is also theta. Both are same. If this angle is theta, then this angle is also theta. Clear? That means this angle and this angle both are same. Then third angle of one triangle must be same as third angle of the another triangle, so that we write both the triangles are similar. If both the triangles are similar, simply we write triangle A1B1P is similar with triangle ABP. If both the triangles are similar, then what happen? We compare side by side. Side by side means simply we take one side of the first triangle, that is A1B1P. That side is A1B1, because A1B1 is perpendicular to the principal axis, divided by, we take side AB. Side AB is also perpendicular to the principal axis. We write AB is equal to, we take PA1 side from the triangle A1B1P, because PA1 situated on the principal axis. Similarly, we take PA side from the triangle ABP, because PA, that is also situated on the principal axis, so that PA1 looks like PA. We compare PA1 with PA. Clear? That implies we write what is A1B1. A1B1, that is the height or size of the image. For height or size of the image, we write H prime, and that is situated above the principal axis. So that according to sign convention, we write plus H prime. Similarly, in place of AB, that is the height or size of the object. For height or the size of the object, we write H, and that is also situated above the principal axis. Above the principal axis means sign is also positive. P to A1, at point A1, image is there. So that PA1, that is the image distance. For image distance, we write V, and here this is the direction of the incident ray, and we also measure from P to A1 in the same direction of the incident ray. If we both are in the same direction, then sign is positive. So that we write plus V divided by PA. At point A, object is there. P to A, that is the object distance. For object distance, we write U, and here we measure P to A, that is in the opposite direction of the direction of the incident ray. Opposite direction means according to sign convention, we put a negative sign. And in place of H prime by H, that is the magnification M is equal to same thing minus V by U. That means for both the mirror means for concave mirror and also for the convex mirror, magnification M is equal to minus V by U, and this is the expression for magnification in terms of image distance and object distance. Now we will derive the same expression, that means expression of magnification, but in terms of focal length and object distance, and also in terms of focal length and image distance. First, we will derive the expression of magnification in terms of focal length and image distance. For image distance, we write V. And you know the mirror formula. You know mirror formula or mirror equation. What is the mirror formula? Mirror formula, that is 1 by V plus 1 by U is equal to 1 by F. That implies we multiply V in left hand side, also in the right hand side, so that this expression becomes V by V plus V by U is equal to V divided by F. That implies what is V by V? That is 1 plus we write V by U is equal to V divided by F. That implies what is V by U? We take 1 to the right hand side, so that we write V by F minus 1. That implies, you know the expression for magnification, that is minus V by U, so that we write minus V by U In right hand side we also take a minus sign, so that is minus v by f, and this is plus 1. That implies in place of minus v by u we put that is magnification m is equal to that is 1 minus v divided by f. That implies finally we write m is equal to, this is f, and here we write that is f minus v, and this is the expression for magnification in terms of focal length and image distance. Clear? Similarly, we will derive the expression for magnification, but in terms of focal length and object distance. Clear? For this, first we write the mirror formula, same thing. And you know the mirror formula or mirror equation, that is 1 by v plus 1 by u is equal to 1 by f. That implies here you multiply u in both the side, in left hand side as well as in the right hand side, so that we write u by v plus u by u is equal to u divided by f. That implies we write u by v plus u by u means simply we write 1 is equal to u by f. That implies u by v is equal to, we take 1 to the right hand side, so that is u by f minus 1. That implies u by v is equal to, if we solve the right hand side, this becomes that is f, here u is there, we write u, in plus 1 we write f. Clear? That implies what is v by u? We write v by u is equal to, we take f to the upper side, that is f divided by u minus f. But expression for magnification, that is minus v by u, so that in left hand side we write that is minus v by u is equal to, in right hand side we write in place of u minus f we write f minus u, and in place of minus v by u we write that is the magnification is equal to m is equal to f divided by f minus u, and this is another expression of linear magnification, but in terms of focal length and object distance. Clear? Then significance of magnification. Suppose in case of concave mirror, you know two types of images are there. In case of concave mirror, two types of images are there. First one, that is real and inverted, and the second one, that is your virtual and erect. And we get virtual and erect image when object is in between, focus f and pole. You also know that. Clear? When object is in between focus and pole, we get the virtual and erect image. And in case of real and inverted image, what happened? Look at the figure. In case of real and inverted image, look at the figure. This one is the real and inverted image. Inverted image means that is situated below the principal axis. Below the principal axis means in place of h prime, we write that is minus of h prime. And above the principal axis, object is there. So that in place of h, we put that is plus h. That means magnification is equal to minus h prime divided by h. So that magnification is negative. Magnification is negative in case of real and inverted image. But in case of virtual and erect image, suppose object is situated in between focus and pole. This is the object. An image is formed. Just behind the mirror. This one is the image. And in this case, image is not inverted. Not inverted means that is erect. So that nature of this type of image, that is virtual and erect, and in case of virtual and erect, object is situated above the principal axis, image is also situated above the principal axis. Above the principal axis means according to sign convention both are positive, so that we write plus h prime divided by plus h, that means magnification is positive. So that finally we write if nature of the image is real and inverted, then magnification m is negative. Clear? Similarly, if nature of the image is virtual and erect, then magnification m is positive. And you know, in case of the convex mirror, what happen? Always a virtual and erect image is formed. If nature of the image is virtual and erect, then you know magnification m is always positive. That means in case of convex, magnification is always positive, but in case of concave, magnification may be positive, may be negative, that depend upon the nature of the image. If nature of the image is real and inverted, magnification is negative, and if nature of the image is virtual and erect, magnification that is positive. Clear? Again, look at the figure. In first case, a diminished image is formed. Diminished image means size of image is less as compared to the size of the object. Size of the image is small divided by size of object. Size of the object is greater as compared to the size of the image. That means a small quantity divided by a greater quantity. So that magnitude of the magnification is less than 1 in case of diminished image. And in the second case, here size of the image is equal to size of object. So that m is equal to h prime divided by h, both are same size. Both are same size means equal to 1. That means if size are same, magnification is equal to 1. For a diminished image, magnitude of the magnification that is less than 1. And in case of a magnified image, here size of the image is large as compared to the size of the object. So that h prime is a large quantity divided by a smaller quantity. So that magnitude of the magnification is greater than 1 in case of a magnified image. Clear? So that we write, simply we write, in case of diminished image, magnitude of the magnification that is equal to h prime divided by h. H prime is small, so that is less than 1. In case of same size image, same size as compared to the size of the object, we write magnitude of the magnification that is equal to, you know the formula, h prime by h, both are same size, so that is equal to 1. Clear? And in case of a magnified image, we write magnitude of magnification is equal to h prime divided by h, and here h prime is greater as compared to h, so that is greater than 1. Clear? And this is all about your linear magnification in case of a spherical mirror. And in the next class, we will discuss about uses of spherical mirror, that means uses of concave mirror and also uses of convex mirror. Thank you.